Okay. Let's see. So it is, yeah. So we're talking about statistics. And first question is, we spent a lot of time talking about probability. What's the difference between probability and statistics? Well, probability starts with a few axioms and then a lot of theorems that proved about these axioms. But probability never asks, is this really relevant for any particular population, any particular data set in life? Next, we are trying to look at real data and try to ask, does it really fit? And if yes, with which parameters? Does this data relevant for any of the probabilistic model that we played with? So probability, all in math. Statistics try to correlate the probability to real sets of data. So given information in hand, what is happened in the what happened once. So I put my hands into the bucket. There are black and white marbles in the bucket. Given that I showed you my hand, what can you guesstimate about what's happening inside this bucket? So we can ask, knowing the distribution, for example, two dice balls. Well, we can ask what is the probability that something happens. For example, what is the probability that the sum of the two dice is 3, given that the first one is 1. But that's all assuming the axioms that we had in mind. It doesn't have to do anything with real data, with real world. What we are going to do next is to talk about the statistics, which is fitting model of data or estimation of the models to the data we have in hand. And of course, that is way too vague without examples. So this is very vague without samples. So assuming that we have a distribution and we want to compute some probability of data or events based on this distribution. For example, x1 ... x10 are distributed with Bernoulli. Let's remind you what is Bernoulli. I have a coin, and this coin have a chance of falling on the face with probability of 0.1 and probability of 0.9 to have a take. And all these events means I toss the coins n times, and the effect of the first while has nothing to do with the results of the first while are completely not affecting results of the second, not affecting results of the third, and so they are all independent. So, given these events, what is the probability that the sum of the ones is 3? That is, that I have face exactly 3 times. Okay, that's probability. What would be the statistics? Giving the data, compute or infer the distribution of its proportion. Example, we observed that x1 is 0 and x10 is 0. What is the head probability of the rest? So probability takes us from the data to the observed data, and inference look at the observed data and giving us some estimation of parameters from which we can play with this process. It will make much more sense with a few more examples. Suppose we toss a coin 100 times. We don't know if it's a fair coin or not, but what do we know? What do we know is that we have 73 heads and 27 tails. What could be the bias of the coin? Is the coin fair or not fair? I don't know, but I can assume some probabilities to it. There are several different explanations to these results. For example, we can, for this data, assuming a random variable that's distributed according to Bernoulli that we just asked, I don't know if I know what is the average out of Bernoulli. Average out of Bernoulli will be the probability of a head plus nothing, plus 0. So just the probability of a head. So suppose we observe n coin flips, x1 dot 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 xn, and we want to estimate what is this pi. Pi is just a bias, was 0.1 in the previous example. We look at the average value of the heads, and that would be our estimation of pi head, the average number of heads. Why is it interesting? Well, because we don't know, just based on these 100 experiments, is this unfair coin or is this a fair coin that just accidentally gave us 73 heads and only 27 tails? Both explanations are legit, but they are not equally likely, which will pushes us to look for what is the most likely explanation, what is in sense, the simplest explanation. Okay, so we can estimate what is a number of heads based on the experiment, and this would be the empirical mean or the sample means. We like terminology, fancy terminology, empirical means. Okay, so let's repeat the experiment multiple times, or we observe the height of n students from the university, and we know that height is usually distributed as a Gaussian. Why is this a Gaussian? Why height is a Gaussian? Well, we talked about it quite a lot in meetings, because we'll assume that maybe the height, there is multiple factors that contribute to height, and each one might be on or off, and maybe they are independent. And we know that when we sum up a lot of terms, they tend to look like a Gaussian. That brings us back to the binomial distribution and the GeoGebra app that I showed you in the second meeting. So, estimated Gaussians. So some oracle came down to earth and told me the height of the students, when I look at the histogram of the height, the oracle posed to me, yes, these heights are distributed based on a Gaussian. But the oracle refused to tell me what is the mean of this Gaussian and what is its standard, its variance. It's the square root of its standard deviation. That's up to me to estimate. And that's where the statistic play into the game. I want to know what the average and what is the standard deviation and various other parameters. So in particular, I can make decision making from the data about possibly extending my trial or making recommendations on movies and so on. So the oracle told me it is Gaussian, because most things in the world following either Gaussian or Poisson, that maybe I'll mention, but I don't know the parameters. So I want to estimate to start with mu. Make yourself familiar yourself. Mu, Greek letter, is the estimated Gaussian, which is just take the height of n students, sum it up, and divide by 1 over n. And oh yeah, these students that you have in your sample, these n students, pick them presumably at random. You don't want as a sample to be influenced by the sample should not be influenced by only pick tall students, only pick short students, obviously. So mu will be this estimated estimated mean, and estimate mu using this sample mean, okay? And our sampled mean, call it mu hat. Okay. And sometimes, feel abbreviated sometimes as X bar. Both are fine. So now we have the sampled mean, our best guess about the average. How can I estimate the standard deviation, sigma? I can assume that if I know the actual sigma, what's the definition of the sigma, of the variance? The variance is the expected value of x minus mu, but I don't know mu exactly. What can I use? The average of the real population. I'll therefore estimate it as, instead of using mu, I'll use my best guess, the average based on the sample, and using this term mu hat, my estimated distance, I can also estimate what is sigma squared. Okay, and of course take the square root will give me sigma. Okay, so my estimation about sigma is just the square root of this term, the average distance from the average. I like this sentence. I'm going to measure the average distance of parameters from the sampled average. Cute. Let's talk about limit theorem. So, limit theorems are the law of large number. What is the law of large number? LLN tells us. It doesn't know about normal distribution or any particular distribution, but it does tell you that if you're taking more and more samples, I take just student at random and take the student average height, doesn't make any sense. Take a pair of students and take their average height. No, take 3 students and take their average height. 4 students, 5 students, and so on each time. Pick larger and larger random subsets. The law of large number tells you that as the size of the subset grows, what happened to its average value? It will be the real average of the whole population. Okay, with theorems that tells you actually how fast you're getting close to the real average, tell you how likely or how unlikely that for a subset you'll be far away from the average of the whole population. So that's a law of large number. Take enough many, how many exactly? Infinitely many students, and you'll get the exact average, but you'll get pretty close to the average, even to the real average, even if you take smaller than infinity of them. Okay? Doesn't say how fast it piles up, how you'd like to have some probability that you're not there yet. Okay, law of large numbers, nice visualization. We are pulling boxes from the, we are pulling either red ball or either red ball or blue ball from the set, and there is some population of the there is some fraction of blue balls and red balls out there. And as we are continuing and asking how many red balls, how many blue balls we have in the sample, and infinity, we will get that it's half and half. Next, the central limit theorems is much more specific. But it tries to say x1 dot 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 xn. They could be Bernoulli variables, Bernoulli coin flips, face or tails. It can be other terms, but what? Whatever happens to x1, independent of x2, independent of x3, they're all independent events, and by the way, each one is rendered according to the same distribution as everybody else. They are independent and identical distributions. Just means that what you did in the first coin shouldn't affect what you did in the second coin. You are not determining whether to use a fair or an unfair coin based on the results of the distribution of, based on the results of the first coin trial. And the theorem tells you, when you look at the average value of n of the set, well, I pick 5 students, and then I pick 5 other students, then I pick 5 other students each time at random, and sometimes the average of these 5 is going to be very high, sometimes the average is going to be very low, but how does this average for any fixed number n, how does this average looks like? Well, this average, the average of the 5 tuples or 6 tuples or 7 tuples will be distributed with average mu. So far, not really surprising. If my samples becoming larger and larger, I'll get the average of the whole population. But each time it's different value, so it's random variable. How is this random variables distributed? It's a normal distribution. So what? Does taking the average of 2 students give me the same information as taking 1 student? Is it distributed in the same way? Not only that it's normal, but the standard deviation is actually the original standard deviation of each individual student divided by n. The larger the set, the more narrow and concentrated this X is. And I thought about it a bit, and I wanted to demonstrate to you what's happening. And let's first see why is this such an important result. Here is my room. You see what's going on? Yes. Here is my room. And I put a sensor, S1. And the sensor reports a temp 1, that's from sensor 1, as every decent sensor should do, plus noise. So how can I know the actual temperature? Noise means I measured the temperature twice. Even though the room has exactly the same temperature in the room, the sensor might report different things, depending on is in the sun, not in the sun, either atmospheric noise or not. That's a random noise also. But you really need to know what is the estimation of the temperature right there in the room. What should I do? Well, place another sensor, S2, place another sensor. Maybe I'll measure it in the same point, but the other sensor replies temp 2 plus noise, but hopefully the noise from that the second sensor suffers is independent of the noise that the first one And now, what will be my guesstimation of the temperature in the room? It would be the average of S1 plus S2 divided by 2. Takes the average of the two sensors, and hopefully, or actually definitely because of this theorem, as long as the noise is independent, the actual temperature, the estimation of the temperature that I obtain by taking the average is closer to the real temperature in the room, closer rather than each sensor independently. Let's see another example. Do I have the left board? Let's say that x1, not related to the sensor, x1 is Bernoulli, it is, plus minus 1, so it would be either minus 1 or plus 1 with probability of half. That would be my first. So it will give, so x1 equals 1 with probability half and minus 1 with probability half. So x1 is a random variable, and what is the average mu? The average of the two values, x1 with probability half, x minus 1 with probability half. The average is of course 0. And what is a standard deviation of the variance? Variance would be the expected value of, in this case, x1 squared, which is what's the possible values. It will appear as 1 squared with, that's one possible outcomes, plus minus 1 squared, another possible outcomes, and I need to average both of them, which gives me 2 divided by 2. So the variance is the variance will be 1. On the other hand, let's say that x2 is distributed in the same way, so x2 is also either 1 or minus 1, each with probability half. And what is a variance if I take x1 plus x2? Let's ask what's the average value of x1 plus x2. Well, x1 plus x2 could be 2, if both of them, x1 and x2, are 1, or it could be 0, if one is 1 and the other one is minus 1, or it could be minus 2. What's the probability that it's 2? That happens with probability of 25%. That happens with probability of 25%. And that happens with probability of 50%. What's the average? Still 0. x1 is 0, x2 is 0, x1 plus x2, the average is 0. And the sum is 0. And if I'll divide by half and taking the average, then instead of 2 over here, I have 1 and minus 1, each with the same probability if I divide it by 2. Great. Why am I showing you all of this? So the average of the sum of the two values distributed just as the average of each one independently. However, how likely it is that I am far away from the optimum? Now I need to take the values of x1 plus x2 squared and ask what is the expected value of the sum, so x1 plus half x1 plus x2 squared, which is nothing but 1/4 times what could be the sum that we get over here, minus 1 squared plus 0, 0 plus, and the 1 plus minus 1 squared. Remember, that happens with probability of 0.25. That's happened with probability of 0.25. So the variance of x1 plus x2 is therefore 1 plus 1 divided by 4 is half. So it's narrower. Makes sense, I hope. Okay, or put it separately, if the limit of the sampled average minus the real average, that will be distributed as the normal distribution with parameters. What should be the average when I shifted it by mu? The average should be at 0, so it should be distributed as a normal distribution, and moreover this subtraction of sigma, that will give me a standard deviation of 1. Okay. Now, in contrast to my toy example, here I am making no assumption about how each xi are distributed, but I do need to assume that they are independent. So what does it mean? Take the samples and keep taking samples of n. How will they be distributed? As a Gaussian. Some samples of n, the average is very small. Some samples of n, the average is very large. But this whole distribution, the larger n is, the larger the sample, the more it's centered toward its average. Okay. So we just repeat the same sentence a few times. If I just sum them up and I don't sample them, and if I don't just sum the xi's, but I don't average them, don't divide by 1/n, then what do I get when I sum up, say, normal distribution? It will be normals. If each if xi is taken from normal distributions like height, their sum is also normal with the, I'll skip this slide, actually. Okay, so parameter estimation. What are we doing in parameter estimations? Big word in nowadays data science. We pose a model of the data, think that there is a model, and we ask how likely it is, and first, if it is a model like Gaussian, like independent variable, sum up as Gaussian, what are the parameters that dictate it? Let's estimate these parameters. Observe the data, typically, hopefully, in the identically and independent distribution, IIDs. We use this term a lot. And what is the probability, if they are independent, really, what's the probability where am I using the independence? Because independence will imply that the probability, in particular, that x1 equal 1, given that x2 equal 1, this probability, the probability is that x1 is 1 given x2 is 1, this probability is nothing but the probability that x1 is 1. The information that x2 is 1 as well didn't increase nor decrease this probability. Okay, and each one is given by the same distribution. So now under these parameters, let's try to estimate the parameters of interest. For the next weeks, these parameters would be the mean and standard deviation. That is. And we'll call either parameters that we are estimating the estimated value, theta hat. And hopefully theta hat, which would be either mu or sigma for the time being, theta hat is either mu or sigma estimated, hopefully we'll approach the real one when we have many sample points. And many different ways to estimate them. But it starts to be a bit abstract. Just to explain what is independent. The probability that A is head, given that the second, I have two coin toys, call them A and B. The probability that in the first I got a head, given that in the second case I got a head. Well, let's assume that these distributions are not the same, implying that whatever we call a die, for example, 10 times, and we call how many times the result is 1. That would be independent and identical distributions. Each outcome of the die will not affect the next one. That's an assumption of the independent, and each roll will have the same probability as each other roll. That's identical distributions. But if I flip coins A and B and they are biased differently, so the probability of the first is head is different than the probability of the second is head, then these are not identical distributions. Or if I first toss a coin and based on the result I decide which coin to use in the second experiment, that may imply that they might each be have the same distribution, but it's not independent anymore. These two results. These two experiments are not independent anymore because what happened in the first experiment affects what happened in the second. You know, problem with trivial things, the more you're talking about them, the less obvious they become. And statistics, the noun, is a function of the data that does not know any unknown parameters. That is, at this point, it is the mean, for example, of the subset that I already estimated it, and that's a sum. I don't need to know anything about the data. The data, the subset, is given in hand. All the variance, all the standard deviation, or other statistics like the order of the values from smaller to larger. Okay, and the term estimator, and I'm with you about being quite confusing that there are a few letters here. What is theta in general? Theta could be either the value of the average, mu, or the value of the standard deviation, sigma squared. Now, theta by itself now can get a hat that refers to, let's estimate either mu or sigma, but only from the samples. So these are real numbers. They are not guesstimated. Okay. And we hope that our estimations will be obviously close to the real ones. And we'll see a few interesting caveats out of it. And so So for mean and for mu hat and sigma hat, these are the estimators of mu and sigma. Okay. So the mean of the weight of the population will be the real mu. That's what we are trying to gain, and the statistic would be the mean of the weight of the sample you start. That would be our statistics. The variable here would be the value of the weight of each person, xi, in the real life or in our sample space. And the sample mean out of it is what we called an estimator. Okay, so define an estimator which is always, we decide that is 0 regardless of the observation. Is this an estimator? Yes. Not. No. What about if but it is definitely an estimator. It is particularly a good estimator? Not really. Why? Because I don't care about the data here. It always returns 0. So obviously it's not. So what properties makes an estimator a good estimator? Let's see. I would like to have consistency. That is, giving enough data, my sample, as I say, is larger and larger, no matter what is exactly my data, but I want my estimator in the limit when n goes to infinity, I want my estimator to go to the real value. If the average, it's average. If standard deviation, it's a standard deviation. But both of them, as my sample space goes all the way to infinity, it should converge to the real value. But that by itself doesn't tell me much. It's a bit weak because it doesn't say that it converges to it fast. So is the sample mean consistent estimation for the real mean? Yes, that's exactly what the theorem told us. That our average mean value, when n goes larger and larger, will go to the actual mean of the whole population. Let's talk about how fast it goes to the real estimation. Let's assume that I pick n students, take their average weight. 10 students take their average weight. Take another 10 students, their average weight, another 10 students, and repeat it enough many times. Each time that I did it with 10 students, I get some error with respect between the average of the sample versus the average of the weight. And I take all these numbers and average them, but to be sure, I'll want them all as positive, so I'll average the square root of the average. That's a mean square root MSE. What do I want it to be? A good estimator, or if I have two estimators and one converge to the real theta faster, it means it's more. This expression tells me it's one estimator is better than the other one because more sample points, more tries of n students out of the population takes the average, more of them are closer to the real value. So the average square distance is smaller in this aspect. And we'll see actually at least two types of such estimators. Okay, so here is a population. Things will become more interesting. Here is a population. Out of the population, I want to estimate theta. And what I'll get is a random sample of size m. You're reading it, so let's increase. And I take the random sample of size m. presumably random, pick at random, and presumably uniformly. Each value is each person has the same probability to be picked in the random sample. And what did I get? I repeated this experiment once with the same M. 1, 2, 3, 4, 5, 6, 7 in this case. I pick another 7. I pick another 7 each time I got a value of my estimator. What do I want the average value versus the real value of theta to be? I wanted many of these values to be closer to theta, and the average distance between the case estimators versus the real one would be smaller. So that's the efficiency of the estimator. What's the average distance between real and distance? But you repeat it n times, and it's very confusing. At each iteration, I pick 10 students that takes the average, or I pick m students, but I repeat picking m more and more. Why? Just to check the quality of my estimator. So we will have a few properties. Here is a mean square errors between the difference of the here are my guesses when my set that I randomly picked is very small, but when the larger set that I pick, the more my sample size, both my estimator should converge to, let's say that the real value is 0. Real value of the average will be 0, say, then what happens? This one will go to 0, which will mean, I have an animation here, which will mean, and we'll repeat to it, that it's possible that some estimator is going to the real value very fast, so it's both efficient and consistent. We will also see that it's possible that we are missing the true value, or we'll see that we are going down to 0, but very slowly, so it's not really efficient. So it would be less efficient than another, but let's introduce yet another property that we need, which is the biasness. Is the expected value of theta is the expected value of the sample space of the sample, let's say, the average, will it really hits the average? That's, if yes, then it's unbiased. But how could it be that that it is biased? What happened if we always hit above the average? Well, if it doesn't go to the real averages, it doesn't mean that our estimator will not go to the average when our sample space when our sample set is getting larger and larger. Of course, they'll go to each other. But if we never guess below the real average, we always guess above the real average, then we call it biased. We overshoot always. So we'll see that unbiased estimator may be less efficient than biased estimator, but at least the average is mu, not more than mu, not less than mu. And other estimators will tend to overshoot or undershoot. So bias estimator, and that sounds paradoxical, it can be still consistent. You are guesstimating, when n goes to infinity, you are guesstimating the real value, but it could be, and it's not hypothetical, it could be that this expected value is mu plus 1 over n, and the sample space. So you're always overshooting the actual value of mu. A bit surprising. Yeah, okay, let's take a break. Or let's call it a day.